219 kilometers. That's the distance a major ocean current shifted in a brand new scientific simulation, and it happened in just 2 years. Researchers studying this system say they've never modeled anything that moves that fast before. And the reason that number is spreading through the scientific community right now isn't just its size, it's what it might be quietly warning us is already starting to unfold in the real ocean. Before going further, it's worth being precise about exactly what this number represents because that precision matters enormously here. This 219-kilometer figure comes from a high-resolution computer simulation, not from a direct measurement taken out of the ocean today. Understanding that distinction from the very beginning is the key to understanding what scientists are actually telling us with this research, and just as importantly, what they're not. The study comes from researchers René van Westen and Henk Dijkstra at Utrecht University's Institute for Marine and Atmospheric Research. Their goal was to understand the relationship between the Gulf Stream, the current flowing up the east coast of the United States before curving toward Europe, and the much larger system it belongs to, the Atlantic Meridional Overturning Circulation, or AMOC. Think of the AMOC as an enormous planetary conveyor belt, carrying warm, salty water north from the tropics, where it eventually cools, sinks, and loops back south deep beneath the ocean surface. That circulation is a major reason Western Europe enjoys comparatively mild winters despite sitting at roughly the same latitude as much colder parts of Canada. And scientists have grown increasingly concerned that a warming climate could push this entire system toward a genuine tipping point. To understand how a weakening AMOC might eventually show up in something researchers could actually observe and measure, the team built a detailed ocean simulation and gradually increased freshwater forcing, mimicking meltwater pouring off the Greenland ice sheet in the real world, until the simulated circulation eventually collapsed completely. What they found while watching that collapse unfold was strikingly specific. As the AMOC weakened, the Gulf Stream's path near Cape Hatteras in North Carolina didn't simply drift north the entire time at a steady pace. It moved slowly at first, then suddenly snapped, covering that full 219 kilometers within just 2 years. Crucially, this abrupt jump occurred a few decades before the simulated AMOC actually finished collapsing, arriving early enough to function as a genuine advance warning, rather than simply a symptom showing up alongside the main event. So has that specific dramatic jump already happened out in the real Atlantic? Based on the evidence available right now, the honest answer is no, not yet. And that distinction matters enormously if you actually want to understand the science rather than just react to a scary-sounding number. What researchers have found in real-world satellite and temperature data, instead, is something quieter, but arguably just as significant in its own right. A slow, steady, measurable trend rather than a sudden snap. Satellite altimetry measurements stretching from 1993 through H2024 show a statistically significant northward drift in the Gulf Stream's position near Cape Hatteras, independently confirmed by subsurface temperature records reaching all the way back to 1965. Altogether, the Gulf Stream appears to have shifted north by roughly 50 kilometers over the past 3 decades, a real, physically observed change, just nowhere close to the scale or speed of the abrupt jump identified inside the simulation. Here's why that distinction genuinely matters, rather than being a mere technicality. In the model, this gradual, decades-long drift is precisely the phase that comes before the sudden, dramatic snap. Researchers describe the Gulf Stream's behavior as unfolding in essentially 2 stages. First, a slow, steady northward creep as the AMOC weakens incrementally, and then, only once the system approaches its actual tipping point, an abrupt, rapid displacement like the 219-kilometer jump identified in the simulation. What scientists appear to be watching unfold in the real ocean right now looks consistent with that first, slower phase, not the dramatic second one. That's exactly why researchers are describing this finding as one of the most useful, physically trackable, early warning signals available for AMOC collapse, rather than as proof that collapse has already begun in earnest. Professor Van Westen has been direct about this point, explaining that the Gulf Stream's physical position is something researchers can genuinely monitor using existing satellite technology, giving scientists a practical, observable proxy for changes happening deep within a circulation system that's otherwise extraordinarily difficult to measure directly. As he's described it, this is something we can actually measure, and the trend already visible in the data strongly suggests the AMOC is indeed weakening in the real world right now, even without that dramatic jump having occurred yet. The study also identified supporting evidence beyond the Gulf Stream's position alone. The Deep Western Boundary Current, a separate current flowing beneath the Gulf Stream, is weakening in both the model and the observational record, and researchers have suggested that weakening current may be part of what's physically forcing the Gulf Stream to detach from the coastline farther north than it historically has. Because the Gulf Stream now sits farther north than it used to, waters in those newly affected regions are warming faster than surrounding areas, a pattern clearly reflected in deep sea temperature data collected across recent decades. It's worth understanding why researchers consider a directly observable signal like this such a genuine breakthrough, given how difficult it's historically been to track AMOC health in real time. Reconstructing the circulation's past strength has traditionally relied on indirect methods, including estimates built from historic sea temperature patterns and salinity records, approaches that carry considerable uncertainty and remain the subject of active scientific debate to this day. Direct, continuous measurement of the circulation itself has only existed since the early 2000s through an observing system called RAPID, which uses moorings anchored across the Atlantic at a latitude of 26.5 degrees north to track ocean flow in the mid-Atlantic and near both the Bahamas and the Canary Islands. Against that backdrop of genuinely difficult indirect measurement, a physical, satellite trackable proxy like the Gulf Stream's coastal path represents exactly what researchers have been searching for since work on AMOC and early warning signals first began roughly 2 decades ago. Other proposed indicators studied in recent years have included changes in the minimum freshwater transport occurring at the Atlantic's southern boundary. But those measurements require considerably more specialized data collection compared to simply tracking where a well-known current physically sits relative to the coastline, something achievable using satellite infrastructure that's already in continuous operation and has been for decades. If you're finding this kind of precise, myth-correcting breakdown genuinely valuable, go ahead and hit that like button. It makes a real difference, helping this channel reach more people who want the accurate version of a headline instead of the flattened, scarier version that tends to spread fastest online. So why does an abrupt 2-year-long, 219-kilometer jump matter this much if it genuinely hasn't happened yet? Because if and when it eventually does occur in the real ocean, researchers believe it would represent one of the clearest, most unambiguous signals available that the AMOC has entered its final approach toward collapse, arriving potentially decades ahead of the circulation actually failing completely. That lead time, while genuinely limited, could theoretically give regions dependent on this circulation, particularly across Europe, a real window to begin preparing, whether that means insulating homes against considerably colder future winters, or identifying more southerly regions better suited for growing food under a fundamentally altered climate. It's worth being clear that even the researchers behind this study aren't claiming collapse is imminent on any specific near-term timeline. Their modeling scenario ran across a full 400-year simulated time frame, and they've explicitly stated their idealized setup doesn't suggest the AMOC will collapse within the coming years, or even the coming decades. What their findings genuinely establishes a mechanism and a specific measurable signature to watch for, not a confirmed countdown clock ticking toward a known date. There's also meaningful scientific debate worth including here, rather than presenting this as fully settled fact. Some researchers examining the study have raised a genuinely important caveat, noting it remains possible for an abrupt Gulf Stream shift to occur, without the AMOC ultimately collapsing at all, in which case the signal would represent a response to weakening already underway, rather than a true predictive early warning. There's also concern that the rate of AMOC weakening simulated in this particular study may be considerably slower than what's realistically expected under accelerating real-world warming, meaning the multi-decade lag. Time identified between the Gulf Stream jump and full collapse could shrink dramatically in practice, potentially arriving too close to an actual collapse to give anyone meaningful time to respond. Stefan Rahmstorf, a prominent ocean physicist at the Potsdam Institute for Climate Impact Research, who has studied AMOC stability extensively, has expressed broader caution about the entire field of early warning research on this topic, noting that the underlying uncertainties around available ocean data remain genuinely large, a concern he says he's held since research into these warning signals first began in the early 2000s. That kind of measured expert caution is exactly why this finding is being treated as a genuinely important new signal worth taking seriously, not as a definitive, universally agreed upon prediction that settles the entire debate. One researcher studying this exact question has noted that it would still be genuinely useful to have a signal that simply confirms a tipping point has already been crossed, even without meaningful advance warning attached to it, though she's careful to add that scientists still don't fully know which category, a true predictive early warning, or a purely after-the-fact confirmation, the Gulf Stream shift ultimately falls into. That kind of intellectual honesty, acknowledging genuine uncertainty rather than overselling a dramatic sounding number, is precisely what separates rigorous ocean science from the flattened, alarmist version of this story that tends to circulate fastest online. At the end of the day, the 219-kilometer figure represents something genuinely rare in climate science, a specific, concrete threshold researchers can now watch for directly, using satellite data that's already being collected continuously along the exact stretch of coastline that matters most. It hasn't happened yet in the real ocean. What has happened is the slower, steadier trend researchers say precedes it in their models, quietly unfolding along the American coastline for 3 decades and counting. Whether the dramatic jump ever actually arrives, and if it does, how much genuine warning it provides before a full collapse, remains one of the most important open questions in ocean science right now. For anyone wondering how research like this actually gets put to use going forward, the value lies less in pinpointing an exact collapse date and more in giving scientists a concrete, trackable metric to monitor alongside everything else already being measured across the Atlantic. Satellite altimetry data covering the Gulf Stream's position gets updated regularly and remains publicly accessible, meaning this isn't a finding locked away in one research team's private data set. It's something the broader scientific community can continue verifying, refining, and stress testing collectively as more years of observations accumulate, which is precisely the kind of ongoing, transparent scrutiny a finding this consequential genuinely deserves before anyone treats it as settled fact, rather than an active, evolving area of research. If you want to keep tracking exactly how this research develops, along with the real science behind every ocean current headline before it becomes tomorrow's viral clip, subscribe to the channel so you never miss an update. Stay curious, stay accurate, and I'll see you in the next one, ready to break down whatever the satellites reveal about that stretch of coastline next.